Yeah. We're going to do some examples about estimating population mean. Yeah, we're going to do that. First off, let's just not use this, and let's just do this so I can do my one slide that I liked. Maybe it'll work. Yeah, okay. Wait. Yes. All right. Okay, so I'm going to share my screen. If you have something you're taking notes on for this class, there's going to be some stuff you might want to add depending on what you wrote down yesterday or didn't write down yesterday. Depends. So I don't need to do that. Why am I doing that? All right. So here we go. 8.3. Second part of the lesson for 8.3, estimating population mean. This is the last section in chapter 8 about estimating with confidence. This is a synopsis of what you need from section 8.3. This is kind of how it's all connected. All right. So these are our key concepts. We have conditions for constructing a confidence interval about a mean. We have to check that it's random. We check the 10% condition when sampling without replacement, and we need to check that the normal large sample conditions are met. The normal large sample is if the parent population is normal, sampling distribution will be normal. We can do all of our work as we want to. The large sample condition is similar to the central limit theorem from last chapter. If the sample is greater than 30, then everything works out. If these two things don't happen, then we have to look at a graph of our sample data, dot plot, histogram, box plot, some graph of our sample data, and make sure that it is roughly normal, meaning it's not really skewed and there's no apparent outliers. If that happens, then we're okay to proceed using our t-distribution. So we have to check these conditions. The inference method that we learned, or that we saw yesterday, was the one sample t-interval for a population mean. It's very similar to the inference method we learned for proportions, where you have your statistic plus or minus the critical value times the standard deviation of the statistic. Same idea. We have our statistic x bar plus or minus t star, the critical value using the t-distribution, times the standard error, otherwise known as the standard deviation of our statistic based on our sample data, which is the sample standard deviation divided by the square root of the sample size. And t star is the critical value from our t-distribution using the degree of freedom n minus 1, one less than whatever the sample size was, and with a c% of the area between negative t star and t star using table B. Right? Table A and table B will both be provided to you in your set of like equations and tables for the AP exam. You'll have access to those. We can also choose a sample size for a desired margin of error when estimating mu. To do this, we must have something to use as the standard deviation, either the standard deviation from a pilot or previous study or from a sample. Right? We need to have a standard deviation to use. We then find the critical value z star from table A, standard normal curve, and we solve the inequality for margin of error for n, and that's the z star times standard deviation divided by square root of n is less than or equal to margin of error. We rearrange that and solve for n. Lastly, whether we're doing a confidence interval for a proportion or a mean, we use the four-step process. This is the roadmap that they expect you to use on the AP exam to make sure that you show all your work and show all your reasoning. You're going to state what you're going to do. What's the parameter, right? We want to find, or we want to estimate the mean, mu, blah, 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 at a 95% confidence interval. That's the statement. Plan, identify the appropriate inference method and check conditions, right? And in that case, you're going to say, if conditions are met, we will use the one sample t interval for estimating mu, or estimating p if it's proportion, right? And then you check your conditions. these three things over here. Once the conditions are met, we do our calculations, which would then be this part. Do your one sample t interval. You find your interval, that's your confidence interval, and you write your conclusion statement. Interpret your interval in the context of the problem. We are 95% confident that the interval from 2 to 5 captures the true mean number of hours students spend on homework every night. Right? That would be a conclusion statement that interprets the interval back to the context. So this is section 8.3 in a nutshell. Anything I can clarify, or does anyone need a moment to write any of this down? And so again, this is like what you need. And now let's just go to this problem. All right, so here's a sample problem that we can solve using what we know from this section. All right. Okay, bye Liliana, thank you. Oh, of course, yes, I'm glad to be able to let you guys rant. It's needed. We're all... yeah, we're all at that point. All right, so we have this crazy context, and to be honest, sometimes the context for the problems in AP and that are in the book, they seem just crazy, or just overly wordy or things like that. It's unfortunately just the way these word problems are sometimes. So we have writers in some fields summarize data by giving X bar and its standard error rather than X bar and the standard deviation. Biologists studying willow plants in Yellowstone reported the results in a table with columns labeled X bar plus or minus SE, standard error. The table entry for the heights of willow plants in centimeters in one region of the park was 61.55 plus or minus 19.03. The researchers measured a total of 23 plants. We want to find the sample standard deviation for the measurements. And recall that the part of our equation that we saw earlier that represents the standard error is the standard deviation divided by the square root of n. And that's our, as we set up our interval calculation, we have a statistic plus or minus critical value times standard deviation of the sample. That standard deviation of the sample is the standard error, is what we use instead. So this is the problem we're going to look at. And I already have the work done because that's how I was doing it earlier. So we're going to look at the work. So this is what would be involved in calculating the standard deviation of the sample. Right. So we start with the plus or minus entry that was in their logbook. We have 61.55 plus or minus 19.03. The 61.55 is the X bar, it's our statistic. Plus or minus the standard error, that is the critical value times standard deviation. Right? Oh, I'm sorry, it's just this equation, I apologize. So we have SE equals S of X divided by square root of N. We write down the parts of this thing that we know. We know SE, we know N, we don't know S of X. So we replace the variables with the values we know, and we solve for S of X. To solve for S of X, we simply multiply each side by square root of 23. That cancels the square root of 23 on the right-hand side, multiplies by this on the left-hand side, and that's the only calculation we have to do. We end up with 91.265 approximately, equaling S sub X, and that's in centimeters as the unit. All right. Is there anything I can clarify on this example? So this one isn't exactly like finding an interval or, you know, calculating a sample size, but it's using the things that we've learned to find a missing value, manipulating an equation. It's kind of just going back to algebra. What can I clarify? Okay. All right. So then we're going to look at my next problem. So again, this is one of the ones with a weird context. We have our big toe problem. A bunion on the big toe is fairly uncommon in youth and often requires surgery. Doctors use x-rays to measure the angle in degrees of deformity on the big toe in a random sample of 37 patients under the age of 21 who came to a medical center for surgery to correct a bunion. The angle is a measure of the seriousness of the deformity. For these 37 patients, the mean angle of deformity was 24.76 degrees. The standard deviation was 6.34 degrees. A dot plot of the data revealed no outliers or strong skewness. We want to construct and interpret a 90% confidence interval for the mean angle of deformity in the population of all such patients. I want to point out what's being asked. Construct and interpret. When you see construct and interpret some confidence interval, that means 4-step process. Right? If you're taking the AP exam, that means you want to show the 4-step process. State, plan, do, conclude. That helps give you the roadmap and helps make sure that you're not skipping any key part. Right? Gets you the most credit. Right? So I'm going to switch back to my OneNote and show the 4-step process for this problem. So we start by stating what we want to do. And we want to find mu. It'd actually be better to say we want to estimate mu, which is the true mean angle of deformity with a 90% confidence interval. Plan, step 2. If conditions are met, we will use a 1-sample t interval for mu. Again, I can use mu here because I defined mu in the statement. If you did not use the variable mu in your statement in your first part here, you cannot use it here in your plan. You need to define what it is first. So we're checking our conditions now as the next part of the plan. Random, well, our patients were a random sample. Condition met. 10%. We can assume that 37 is less than 10% of all such patients. This is an assumption we get to make because they didn't tell us the size of the actual population, so we can't check it. They're asking us to find this interval. So that information being all that we have, we're just going to assume that this is going to be okay. But we still have to say that. And then this meets our large sample condition, and it is equal to 37, which is greater than 30, so we can use the t-distribution. So all of our conditions have been met. We've finished our planning stage. Next, we do the math. So in this case, we know x bar, it's 24.76. We know the sample standard deviation is 6.34. We know that we want to find a 90% confidence interval, which gives us 36 as the degree of freedom, which means we have to use 30 from table B, because that is the closest degree of freedom listed that is not greater than 36. Right, and remember, we got to use Price is Right rules. We got to get as close as we can, but we can't go over. That gives us the T star of 1.697. And N equals 37. That is our sample size. Does anyone want me to show how we get this T star value using table B? Okay. Let me get my table B. right, here is table B. And we have 36 as the degrees of freedom, right? 36 does not exist on here. It goes 30 or 40. I can't go over, so we're going to use 30. I do not want to put a link to that. I want to So we'll use 30. And we want 90% confidence, which we'll find down here on the bottom. We're not really worrying about this top row of tail probabilities at this point. We're not using it in this chapter. Right, and so then we find the intersection of these two is 1.697. And so that is our T star value. Yeah, there we go. Right, this we get by following this bad boy up here. Would be. Well, that highlighted more than I want, but that's okay. So anyway, we get 1.697. And that's our T star. Now we can do our calculation. We find the interval. Right, we start with x bar 24.76 plus or minus T star 1.697 times S sub x divided by square root of n, 6.34 divided by square root of 37. When we subtract the standard error, not standard error, margin of error, 1.697 times 6.34 divided by square root of 37, we get 22.991. When we add the margin of error, we get 26.529, and that is our interval. Make sure you're finding an actual interval. If you get one value as your solution, you've missed part of it. You need a lower value and an upper value. Those make up the boundaries of your interval. That allows us to now make our conclusion statement. Right? We are 90% confident that the interval from 22.991 to 26.529 degrees, I should have put the word degrees in there, captures the true mean angle of deformity in the population of all such patients. Okay, and so kind of the trick here to make sure you get the right context and everything is you just fill in the blanks of a sentence frame here. We are 90% confident, fill in 90%, that the interval from, fill in your two numbers, this to this, and give the units, captures the true mean, and then we refer back to the original question. We just steal the last part. The true mean angle of deformity in the population of all such patients. Slap that on at the end. Now we've gotten the correct context. Right. What can I clarify? What can I explain better?
Can you re-explain how you got the two different numbers? Like you said the margin of error or whatever. Did you like subtract?
Yeah.
Like, can you tell me?
Yeah. Let me get my scribbler out here. So this here says plus or minus. That means I'm actually doing two calculations in this one equation. I go through this equation one time and I add what's on the right of that sign. And then I go through a second time and I subtract what's on the right hand side of this sign. So I do 24.76 minus 1.697 times 6.34 over square root of 37. and that gets 22.991. And then I go through the same calculation and I add. And we get 26.529. So when you see this symbol, it means do this thing twice. Add the number to the right once on the first time, subtract the number on to the right of that symbol the next time. And that gives us those two boundaries of the interval. Does that answer your question? Does that clarify?
Yeah, thank you. And then can you explain what you, like, when you subtracted the 37 minus 1 for the freedom or whatever, can you re-explain why we have to do that and like the concepts of finding the table? Like, you don't have to show me the table, but like the rules basically.
So degree of freedom is always just one less than your sample size. There's a reason for that. I just don't remember what it is. I believe it's so that you're guaranteeing not to overestimate. So subtracting 1 allows us to be makes sure that we stay within the confidence that we want. I believe that's part of the reasoning. Yeah, it's like a safeguard of so we don't overestimate. And so that's how we find the degrees of freedom. And then the rule, like I said, is Price is Right rules, as close as you can get without going over. So on our table, on table B, 36 is not a value available on the left-hand column. And that's in any table B you go and find. They all are listed very similarly. They go from 1 through 30, listing every number, and then it goes 40, 50, 60, I think 80, 100, 1,000, and infinity or something like that. Like it jumps. And it's because the difference between these values as you increase from these levels, you can see it's not changing much in each column. Right? And because it's changing so little between these jumps in value, right? For 50 and 60, it's actually like at 50%, it's the same. Almost the same, almost the same. The change is not that much anymore. And so they're like, well, the table is estimating with this, right? If you want to get a little more close, you have to use your calculator. So, what is it? Stat, no. Nope, that's not our one. Right. So this function, the inverse t function, finds the t star value for you based on the area, right, which is the area to the left of a t value and the degree of freedom you have. So with a 90% confidence interval, the area is actually going to be 95. So we're going to use 0.95. I believe if I'm remembering how to do this correctly. Our degree of freedom for this example was 36. So I can actually put in 36. It's out for me. All right, and so we get 1.688, which is a lot different actually. I may not have done that correctly. Need to look at my example again. Sorry, I tried to learn how to do this earlier today, but decided I wasn't super good on it yet, so I didn't show it today. Sorry, a lot of these things I just refer to, I default to pencil and paper, because that's what I'm comfortable with. I used one of these calculators in college. My stats teacher didn't let me use it in tests, so I don't know how to use a lot of these things. We were only allowed to use like a TI-30. Yeah, let me actually pull up the video that shows how to do it because I screwed it up, I think. So give me a second. I have the video. Actually, everybody has the video. I have it on Z Resources. That's not what I wanted. I clicked the wrong one. I want notes and resources. So yeah, there's lots of stuff for 8.2 and 8.3, guys. There's like 10 AP Daily videos that apply to that section. It's crazy. But anyway, calculator videos. Inverse T on the calculator. So this is the one that shows us how to get a T star value based on a confidence percent and degrees of freedom. I need to make this thing let me use the audio though. There it is. Let me know if you guys can hear it when it starts.
Hello, I'm Lena Taro. I'll be showing you how to find T-star values on the TI-8384 calculator. To do this, we'll hit second, then vars. Notice above in blue it says distribution, and choose inverse T. This is similar to the inverse norm command for finding Z values. The command structure is to enter the area to the left of the cutoff. So if we're talking about a 95% confidence interval, that means we have 2.5% in each tail of the distribution. So 95% plus 2.5% would be 97.5%. Then we'd enter our degrees of freedom. Let's say our degrees of freedom is 11 because our sample size was 12. So our T-star value is about 2.2. Notice I had to remember the command structure. However, if I have my calculator mode set with the stats wizard on,
your guys' calculator should be defaulted to ask you for like the prompt that you saw on my calculator. This is a different version of the TI-84 that she has here. It's the color one and it has more bells and whistles, but same concept. So I'll continue here.
Then it'll give me a template that I can fill in. To turn the stat wizard on, you'd hit mode, come here all the way to the very bottom and choose on. Let's run that command again. Second, distribution, inverse T. Notice a template is here for us. I enter the area and the degrees of freedom and choose paste. I don't have to remember the command structure if I have my stat wizards turned on.
All right, so that's again kind of demonstrating how to use the calculator to find your T-star value. The value that your calculator finds may not match to the value on table B. However, that being said, usually there will be two versions of an answer provided. You know, like if you look at an answer in the back of the book, it might give the value that you would get by using table B or table A, for instance, and then another solution that would be found using technology. They're not always going to match exactly the same. Sometimes they do, but sometimes they don't. So just keep that in mind. If there's a difference between an answer you have and an answer that you see somewhere else, that might be the reasoning. All right, was that helpful? Did that help you guys with the calculator? And I have those videos. That's posted in here with our calculator videos in the resources. So yeah, there's a lot of resources.
I have a question.
Yes.
So I know that like the freedom number was 36. Is there a reason why in table B you chose to pick the 30 column instead of the 40 column? And if you were to pick the 41, would your answer be considered wrong?
So if you used 40, your answer would be considered incorrect. You might still get something that's really close. Like you could be kind of right by accident, so to say. Especially because like as we move down here, the numbers aren't as different. There's a big difference between 1.697 and 1.684, relatively speaking. So using 40 is going to produce a different result. We use 30 because we have to err on the side of caution. So we can't overestimate, right? We don't want to overestimate what the interval is. So we need to use the lower degree of freedom available. Right? That's the default. If your number isn't available on the table, you use the greatest degree of freedom listed that is not larger than the number you have. So in our case here, the number we got, a degree of freedom, was 36. The largest number on table B available is 30, because that's the largest number that is not greater than 36. Right? And again, the reasoning is if I round it up, I'm overestimating, and I don't want to do that. I'd rather be cautious.
That makes sense. Thank you.
And I just think of it as Price is Right rules, right? When you play the Price is Right, if you guys have seen the Price is Right, the goal is to get as close as you can without going over when you're guessing the price of something. So this follows that idea. Get as close as you can, but you can't go over. Yeah. All right. Cool. So, good. Those are the two like big examples that I had planned for today. Those are the ones that involve the most like math and calculation. So the other thing is, yes, please keep in mind, I have a ton of resources here for Chapter 8. We have, like I said, there's a lot of AP Daily videos for sections 8.2 and 8.3. The first half of the videos are all proportion, the second half are all mean. There's the study guide, presentations, worked examples from the textbook. Right? These are all for 8.2 and 8.3, which are the main things in Chapter 8. 8.1 is just our introductory thing. It goes over the main concepts, and then this is how they apply to proportions and means. So don't forget about all the resources that we have in here. Also, our multiple choice and free response questions are posted. The multiple choice is 10 questions again. And again, do it if you don't do well. Look at your results. I have it set up to show you whether your responses were correct or incorrect and to provide the feedback for those responses. It won't tell you what the correct answer is. That setting is not enabled, but it'll tell you if you're right or wrong. And then the free responses actually was finished up right before class. I've adjusted this so that at the top here, it's basically the study guide for Chapter 8. All right, it's kind of like all the main formulas and concepts from each section of the chapter. Right, so it's like a little study guide for you there. Then we have our questions, the free response questions. There's 2. It's essentially, I wrote the questions, so these don't exist anywhere online. And each of the questions, one for a proportion, one for a mean, you need to construct and interpret a confidence interval, right? Decide whether or not your interval supports a claim. And then using the same context, determining an appropriate sample size for a given margin of error and percent confidence. Both questions are asking essentially for you to do the same steps, just applying the correct formulas for either proportion or mean. Right. And then we have our self-assessment reflection. It's a different question on the reflection. I'm trying to change the question each time. So yeah. So you guys are the first ones to get a preview of that. And it's available, published, and ready to go. Yeah, that about sums it up, guys. Stop sharing my screen. So yeah, that's it. Once again, thank you guys for your time and for answering my questions and humoring me and what I'd like to know. And thank you for venting and doing that. If there's any other questions you guys have, you have any other comments, concerns about the class, about school, about whatever, college, I'm happy to talk about my experience in there too. Stick around, let me know. Otherwise, you guys are done. Enjoy the rest of your week. Have a great weekend, and I'll see you on Tuesday next week. Yeah. We'll leave it at that.